Imagine you're running one of the world's largest short video advertising platforms, and you want to harness a large language model to understand your users better. The language model knows a tremendous amount about the world, about products, about why someone might buy a bedspread versus a sundress. But your recommendation system speaks a completely different language, one of user IDs, item IDs, click probabilities, and conversion rates. How do you get these two worlds to actually cooperate rather than just awkwardly coexist? That's the puzzle the team behind Taiji, from Kuaishou, set out to solve, and they've now deployed their answer to over 400 million daily users. Let's set the stage. There are three popular ways to bring large language models, or LLMs, into recommender systems. You can have the LLM directly generate recommendations, you can scale up your ranking model using LLM architectures, or you can use the LLM-as-Enhancer, generating rich semantic features that feed into your traditional recommendation backbone. That third approach has dominated industry deployments because it decouples the expensive language model from real-time serving. But even within this enhancer paradigm, there are two persistent headaches. The first is during supervised fine-tuning, where you train the LLM to produce chain-of-thought reasoning about why a user might want a particular item. Unlike math problems, recommendation reasoning is open-ended. There's no clean way to grade whether a reasoning trace is good. Prior work either trusted big teacher models blindly or used crude heuristics. The second headache shows up during reinforcement learning, where you try to align the LLM's outputs with what actually drives clicks and purchases. People use a mix of semantic rewards, meaning does the predicted item match the real one in meaning, and preference rewards, meaning does the recommendation actually convert. The problem is, they combine these with fixed, hand-tuned weights, which is like trying to drive a car with the steering wheel locked in one position. Taiji attacks both problems. For the fine-tuning stage, the authors introduce something called reverse-engineered user preference reasoning. The clever trick here is that instead of asking the teacher model, a 32 billion parameter QWQ model, to predict what a user will buy next and then explain why, they give the teacher the actual ground truth purchase up front and ask it to construct a plausible reasoning chain that leads to that known outcome. Think of it like a detective novel where you already know who did it, so the explanation has to be coherent and consistent. This produces much higher quality reasoning data because the destination is fixed. But even reverse-engineered reasoning can be sloppy, so they add a filter called open-ended rejection sampling fine-tuning. For each user prompt, they generate 3 candidate reasoning chains, and then they score each one using perplexity. Specifically, they ask, given this reasoning chain plus the user profile and history as context, how confidently does the model predict the actual ground truth item? Low perplexity means the reasoning genuinely flows toward the right answer. High perplexity, as in the paper's example where the model reasoned about summer fashion. But the user actually bought a bedspread means the chain is logically disconnected from reality. They keep only the chains below a threshold, set at the median of the perplexity distribution, and use those to fine-tune a smaller 7 billion parameter DeepSeek R1 model. Now comes the heart of the paper, the reinforcement learning stage. They have 2 reward signals. The semantic reward measures cosine similarity between the embedding of the LLM's predicted item and the embedding of the actual purchased item using a Quen embedding model. The collaborative reward comes from the production ranking model itself, which scores the predicted user item pair with a click-through and conversion rate probability. These 2 rewards live in completely different worlds, one in language semantic space, the other in collaborative filtering space. Combining them with static weights, the authors argue, fundamentally cannot trace out the Pareto front, which is the curve of optimal trade-offs where you can't improve one objective without sacrificing the other. Their solution, Pareto Optimal Policy Optimization dynamically adjusts the weight on each reward at every training step. The full version uses gradient alignment. At each iteration, they look at the gradient that each reward would push the policy in. If a reward's gradient is well aligned with the combined direction of all rewards, meaning following it helps everyone, they crank up its weight. If a reward's gradient conflicts with the others, they suppress it. They show this update rule is actually a mirror descent solution to a bi-level optimization problem, and its stationary points provably sit on the Pareto front. Here's the elegant analogy. Imagine two people rowing a boat together. If they're paddling in compatible directions, you let both pull hard. If one starts pulling sideways and would tip the boat, you ease off on that one. That's exactly what the gradient alignment indicator does. Computing gradient inner products at every step is expensive for industrial scale, so they introduce POPO Lite, a clever approximation. Instead of looking at gradients, they look at the coefficient of variation of each reward across a rollout group, meaning the standard deviation divided by the mean. The intuition is that if a reward still varies a lot across different sampled responses, the policy hasn't saturated on it yet and there's still room to learn. If the variance has collapsed, the policy has essentially mastered that reward and should focus elsewhere. This requires only forward pass statistics, making it nearly free to add to the training loop. Once the LLM is trained, they deploy it in two ways. They use it to generate reasoning and predicted items for each user, embed those outputs, quantize them into sparse ID features using product quantization, and feed them into the ranking model. They also use the embeddings to retrieve the most similar other users, pulling in those users' recent behavior sequences as cross-user collaborative signals. The results are striking. On their offline benchmark, the full Taiji pipeline with POPO improves category-level accuracy by over 50% and CT-CVR by nearly 12% compared to the untuned DeepSeek R17B backbone. Notably, the 7 billion parameter student model surpasses its 32 billion parameter teacher on most metrics. In a one-week online A/B test on Kuaishu's ad platform, with 10% of traffic on each arm, Taiji lifted advertiser value by 2.83% and platform revenue by 3.30% overall, with the long-tail user segment seeing gains over 5%. For an ad platform of that scale, those are massive numbers. A few honest caveats worth surfacing. The Pareto optimality guarantee rests on a mirror descent interpretation that holds at stationary points, but in practice, neural network optimization doesn't reach clean stationary points. The reward weights are also constrained to sum to 1 across just 2 rewards, so the Pareto frontier they're exploring is fairly low-dimensional. The semantic reward depends heavily on the quality of the Quen embedding model, which becomes a hidden bottleneck. And there's an interesting result buried in the ablation table. POPO Lite actually outperforms full POPO on title hit rate at 100, suggesting that the more expensive gradient computation doesn't uniformly help. Finally, the offline simulation environment for the collaborative reward uses the production ranking model's own predictions, which means the LLM is being trained to please a specific scoring function that itself has biases. Now let's walk through some questions you might have after hearing all of this. First, why does reverse engineering the reasoning actually produce better training data than just asking the teacher to predict directly? The intuition is that open-ended recommendation has an enormous output space, so a teacher model freely guessing will be wrong most of the time, and wrong reasoning followed by wrong answers teaches the student nothing useful. By fixing the ground truth answer and asking the teacher to justify it, you guarantee the destination is correct, and the teacher's job becomes the much easier task of constructing a plausible path. This is similar to how it's easier to write a proof when you already know the theorem is true. Second, what would happen if you just used static reward weights but tuned them carefully on a validation set? You could find 1 point on the Pareto curve, but you'd be stuck there for the entire training run. Early in training, the semantic reward might be the dominant signal because the model needs to learn basic alignment, while later the collaborative reward should take over to refine fine-grained preferences. Static weights can't follow this curriculum, which is why the authors see consistent gains from adapting them throughout training. Third, why does POPO Lite, the cheap version, work nearly as well as full POPO when it uses such a simple signal? The coefficient of variation captures something fundamental. A reward with high variance across rollouts still has discriminative information, meaning the policy can still tell good responses from bad ones along that axis. Once variance collapses, the policy has essentially saturated, and pushing harder yields diminishing returns. This signal correlates strongly with what the expensive gradient alignment computation reveals, but you get it almost for free from statistics you're already computing. If you're building large-scale recommendation systems, the most directly transferable idea here is the dynamic multi-reward weighting scheme. Production ranking systems almost always optimize multiple objectives like clicks, watch time, conversions, diversity, and creator fairness. Most teams combine these with static weights that someone tuned 6 months ago and nobody wants to touch. POPO Lite in particular is appealing because it requires only the reward statistics you're already logging, no extra backward passes, and it would let your multi-objective ranker adaptively shift focus as different objectives saturate or destabilize. You could imagine plugging this into any multitask learning setup where you're balancing engagement against monetization against long-term retention. The reverse-engineered chain of thought trick also has practical legs. Many recommendation teams are now experimenting with LLM-generated user profiles or item descriptions to enrich sparse features and cold start retrieval. Anchoring the LLM's reasoning to known ground truth interactions during training, rather than letting it free associate, would produce much cleaner enhancement features. And the product quantization step that converts dense LLM embeddings into sparse IDs is exactly the trick you need to make LLM features compatible with the embedding tables and feature crossing layers that dominate production ranking architectures without blowing up serving latency or memory.